episode 7. So starting from this episode, we're going to do a 2-episode series about GPU and hardware acceleration. And so one note is that this particular notebook and next one is going to require CUDA dependency. So you will need to run the relevant part on a CUDA 11 environment. If you don't have such an environment, it's also fine, as you can go and follow along. And actually, the particular sum over code generation content also generalized to non-CUDA content that we will also mention later. So this is part 1 of GPU acceleration. So I'm still using this Colab environment, except that I'm using it in GPU enabled. So right now, if we take a look, there's a Tesla P100 GPU in here that I'm going to use today to demonstrate some of today's process. To begin with, we're still going to import some of the necessary dependencies. So GPU is kind of an exciting topic in a sense that I still remember when I started working on deep learning and building machine learning systems. The first thing I did was hack a very old GPU card and bringing in deep learning models onto those devices. One of the main difference between a GPU and a typical central CPU processor that you might see in your mobile phones or on your laptop is that GPU themselves are massively parallel. So this is kind of like an illustrative diagram of what a GPU architecture looks like. So normally you will have a global memory. So when you buy a GPU, it says you have 24 gigabytes of DRAM or HBM. This is the global memory part. And then within the global memory, within a GPU, there are multiple what we call stream multiple processors. So if this is a GPU, actually we'll have multiple of those stream multiple processors that sits on this GPU card. Each of the stream multiprocessor contains a group of compute cores in CUDA. They call it CUDA cores. That can be viewed as an independent execution unit that allows us to execute some related computations on the respective cores. And effectively, each of a stream multiprocessor kind of corresponds to this kind of global unit. And another interesting thing about GPU is that within each of the stream multiprocessors, it have explicitly managed what we call shared memory that can be accessed by all those cores. So this is this is a typical NVIDIA GPU or AMD GPU architecture. If you look at some of the GPU architectures, some of them may not have shared memory or have other special things. But normally, you can view it as this kind of two-level structure where you have global memory, you have stream multiprocessors, and you have each of a core that can execute the code in a reasonably independent fashion. So normally on a GPU, you have multiple of those stream multiprocessors. And one of the key interesting thing about GPU is it's massively parallel. So if you look at a typical NVIDIA GPU, it can contain more than thousands or sometimes tens of thousands cores. That means that effectively you can execute so many things together, right? Comparing to a typical CPU you can get up to 64 cores at most if it's a server class CPU. So that's a huge amount of difference. On the other hand, the type of operations that GPU cores can perform is also somewhat limited. Also, it can actually serve most of our machine learning workloads. So now we've introduced this generic overall architectural view of the stream multiprocessors. Let's come back and then talk about how we normally program a GPU. So conceptually, when we have a GPU at hand, what we do is we try to map the computations onto a group of threads. So in this case, we have one thread, a program that describes one thread that get mapped onto one of the cores in here. And then multiple threads can be grouped together, and each of these multiple threads can form what we call thread block. And during execution time, this thread block get mapped onto a stream multiprocessor effectively onto here. And then finally, we can launch multiple blocks that can get mapped to either the same stream multiprocessor or different multiprocessors. So effectively, in here, each of a block in here kind of can expand onto a list of threads, and another block in here can also expand to another list of threads here. Okay, and this is conceptually, how we can program this. And now let's start to see a concrete example of how we can use tensor and some of the things we learned in the past lectures to also perform some of the GPU optimization on the GPU that we have on this notebook. So first of all, what we do is we can define our vector add operation program. So in this case, this is a tensor program. Recall that we have buffers, these loops, and the particular operations. So in this case, we are simply taking two vectors and try to add them together. In order to map it onto GPUs, remember that we have the ability, the GPU contains many threads, right? So the idea is that we want to try to map them onto the thread blocks and threads. So in order to do that, let's first go and split the loop I. So right now we have only one loop, and in the next case, I'm going to split it onto two components, like the inner and outer loop in here. And then what I'm going to do is I'm going to map it onto the thread indices of a GPU. So normally in a GPU program, for each of a thread, it can be identified by two indices. I'm using CUDA terminology here, but if you are familiar with other GPU terminology like OpenCL or SYCL or Metal, there can be a slightly different terminologies, but usually they translate to each other. The thread indices refers to the offset of the thread. For example, in this particular case, within a thread block, the first thread index is 0, 1, 2, and so on. So these are like thread indices. And then the block indices refers to the offset of each of the thread blocks. So effectively, a thread index and a block index help us uniquely identify a thread within the kernel that we launch. What we can do here is we can try to bind the iterators onto block index and thread index here. So if we do that, and you'll find that in this particular case, the for loops contains what we call thread binding construct that indicates that, hey, this particular loop is going to be binded to a GPU thread. And so effectively, when we launch this, we are not executing these two for loops. So these two for loops is going to be it simply maps onto the environment GPU indices that's available on that particular thread. And one interesting thing is that you can find that all the threads actually is running the same program, with the only difference come from the indices that you have on that particular thread. For example, the block index and thread index offset that on that particular thread that all yeah. So now that we have this program that bounded those iterators onto GPU threads, moving next, what we can do is we can go and build and test out the resulting function on a GPU. So in this case, we are running a similar procedure, with only differences that we're trying to set the target in here as CUDA, so that we will be able to build the particular module on the CUDA environment. And we are also creating, the input random vector in here, and we are copying them onto, in this case, two ND arrays on the CUDA environment, and we're also allocating an output ND array in here. Okay, and running next, the way we invoke this generated GPU kernel is the same. It's the same way we invoke the original previous tensor functions that we had in the past lectures. So all you need to do is to pass in 3 ND arrays, with the only difference that we are going to pass in the CUDA device context in here instead of the normal instead of a normal CPU context we had in the past lectures. We can print out to say that actually you'll find that the corresponding elements did add up together. And we can also go and use the NumPy assert or close to confirm that actually all the results match up. Okay, so far so good. So that's a GPU example 101 that help us to go and try out one running example of adding two vectors together. Okay, moving next, let's move towards another example that's slightly more complicated. So in this case, what we're interested in is we are interested in taking this input array and trying to do a window sum. So the idea is that for each of the element, I'm going to look at a window of size 3 and add those three elements together. For example, if it's 1, 2, 4, and the result is going to be 7 on this particular element. So it's kind of like a tiny version of convolution with weight of with all the weights equals 1. Okay, so here is our window sum program that we can write out in tensor with a simple loop that loops over the output space, and we are going to try to add three consecutive elements together. To run this window sum on GPUs, again, we can try to do the thread splitting and try to go and bind the corresponding elements onto the thread index and block indexing here. One of the things we noticed is that actually, in order to optimize this program, one thing that we want to notice that, if you look at the GPU, overall GPU memory hierarchy in here, you can find that each of the threads have a shared memory that we can leverage. When we are trying to go and run this particular program naively, right, you will have each of the threads go and read three elements in here, and this neighboring thread is going to read the other three elements, a neighboring thread is going to read another three elements, and you'll find that actually there are quite a lot of overlaps, right, of each of the elements that are being reading here. So for example, if I'm going to read this, because this is going to read these three elements, this thread is going to read these three elements, and this shadowed area are the areas that are overlapped between the reading region between these two elements. Okay, so how can we go and further optimize it? So one of the things that we can do is we can try to leverage the shared memory in here that's being shared across multiple threads. And the idea is that instead of trying to have each of the threads go and directly read from an input, let's try to collectively get all the threads to read the input together. For example, assuming that I have 4 threads in my group in here, and you'll find that actually I only need to read this amount of elements, and if I'm going to go and read it individually, I will have to read 4 times 3 times from a global memory. But if I try to directly read this region in this region, that by considering the possible overlaps, I only have to read 4 plus, I guess it's 4 plus 2 elements, right? So this equals 12, that equals 6. So I almost get a half reduction in terms of reading the data from global. And another thing that I forgot to note is that the cost of data loading, just like when we introduce the CPU optimizations, there's always the memory latency and throughput cost of loading from the lower layer of memory hierarchy. Similarly, the cost of loading from global memory to shared and shared memory to the registers are very different. The cost of loading from global memory to shared is much larger usually than the cost of loading from shared memory to each of the threads. So as a result, usually we do want to be able to fetch the data first, right, onto the shared memory, then try to run computation there. Of course, one of the trade-off here is that each of the GPUs have limited amount of shared memory, so we kind of need to plan to use that a bit wisely. Okay, so in order to do that in our tensor program, what we can do is we can try to create a scope called shared. In this case, we are using this cache read construct. Effectively, what I try to do is try to create another stage. So if you look at the original program, the producer-consumer graph looks like if you are reading from A and you are trying to run computations on B, and effectively in here I'm trying to create what we call a shared program, and then going to read that onto B. Okay. And another thing that that we do here is we are also trying to put the shared memory loading at a particular region. In this case, I'm putting that under the block index in here, so that in other cases, we might want to put them on the thread index. Actually, in this particular case, putting it on the thread index is also fine. Let's try to see if that's the case. So putting it on the thread index is also okay. Okay. One thing that we want to, one thing that we do want to note though, is that because it's a shared memory, right? And as a result, we still need to re-specify how each of us thread is going to read which element of the shared memory. If you look at this program, you can find that we do have, this is the shared, so we might need to, because this is imperative, we need to run it over again. Try. Yeah, so in this case, because this is a shared memory, although it's already in the thread index regions, we still need to re-specify how we're going to read each element of a shared memory, because this memory is being shared, and the thread binding patterns can be different. Okay, so the way to, and another thing you notice is that as of now, I1 is in the thread index. It appears on the normal computation block, but I1 does not appear in here, right? So effectively, if we naively run this particular program, each of the thread is going to go and trying to attempt reading, and it's going to go and trying to attempt read most of the 100 elements altogether. So in that sense, it's not a very efficient way. Effectively, thread 0 is going to go and read all of them. Thread 1 is also going to read all. So we want to distribute the work a bit among the threads in the computation. What we can do is we can try to get the loops here, split it, and then rebind the thread. So in this new program, what's happening is that you can find this is a reading region. And that one thing you notice that this thread index binding appears multiple times, but within our computations, because all the axes directly maps to the thread index, right? So we are only going to count it for one time. And effectively, what it says is that I'm going to distribute the loading task of the A shared across multiple threads. In particular, this program will try to distribute a loading task of A shared on from for example, I could assign thread 0 to read this, 1 to read this, 2 to read this, 4 to read this, and 0, 1 again. So at most, one thread have to read 2 elements from the shared memory, as opposed to reading all the elements, or reading the corresponding elements they are interested in. This is a technique called cooperative fetching, because each of the threads are trying to cooperating with each other to fetch the data that we collectively needed. And this is a very commonly used technique in GPU programming to fetch the necessary data from the external global memory onto the local shared memory that we're interested in. Okay. Finally, we can actually go and inspect a bit what does final code look like. So right now we have this TensorIR code in here, and what I'm going to do is I'm going to try to build it to a CUDA program and try to print out the source code. So in this case, when we build the CUDA code under the hood, we try to generate 2 components in here. The one component is what we call host driver that calls onto the GPU driver and it launches the kernel. And then the other component is the CUDA kernel that runs the corresponding computations. The following code prints out the corresponding CUDA kernel, and in order to run this CUDA kernel, it still needs to be driven by the host program, but the CUDA kernel itself kind of is a good way for us to tell, what is the final code looks like. So if you look like this code, you can find that, hey, we have a shared memory component in here. There's a shared memory loading, And you can realize that there's no shared memory loops in here, right? The shared memory loops directly translate onto the thread index in here. Once we load things onto shared memory, we will run this windowed computation, which if you scroll over, you will find that hey, this is a windowed computation over 3 elements in here. Another thing that I want to note in here is that if you look at the size of shared memory, it's actually smaller than the original size, which is 127. And this is a reason. This is because during the build process, the overall program will try to compact the memory buffers during the build so that it only try to use the shared memory size in corresponding to the size of memory that we touch in the intermediate stage. So normally that is more efficient than directly allocating the bigger shared memory, which actually sometimes runs out of memory of the GPU capacity. Okay, so far up until now, we've talked about 2 concepts: how we can go and bind things to GPU threads, and how we can leverage shared memory and do cooperative fetching to bring data from global parts onto this stream multiprocessor shared memory, and then run computation there. And so far we've talked about how to build this entire process in a CUDA platform. Typical machine learning compiler allows us to support multiple kinds of hardware platforms. For example, we can also generate the OpenCL code by taking a different target string. So in this case, I'm passing OpenCL here, and if you have run OpenCL kernel before, you can find that this is the syntax that writes out the same kernel in OpenCL. The syntax is roughly have a one-to-one translation. Actually, if you read a CUDA kernel, you will be able to tell that hey, there's a roughly one-to-one mapping that allows you to map the original CUDA kernel to the corresponding OpenCL kernel in here. And we also support other targets like metal, other cases. Let's see if metal is enabled. I'm not too sure, but okay, yeah. So this is the metal kernel that allows you to run the same program on Apple GPUs. Okay, so that's the first part. Now we talk about some of the GPU basics. Moving next, let's start to try out running our tensor transformations and try to optimize a slightly more complicated program, which is matrix multiplication that we have studied in some of the past few lectures. So this is our original tensor program that corresponds to 1024 matrices, A and B, and multiply together, and we are going to load that onto C. So we can run a few transformations to optimize this and try to map that on the GPU. The first technique that we're going to use is what we call a local blocking or register blocking. The idea is that for each of a thread, we're trying to load, instead of computing each of the element, we're trying to compute one sub-matrices at a time. So for example, I could choose to compute 4x4 sub-matrices here together. So the idea is, for example, each of the iterations, what I'm going to do is I'm going to read in one stripe of this input from A, another stripe from B. Recall that our matrix multiplication operations formula is Cij equals sum k aik times bkj. So in here, I'm trying to compute this for a subregion of I. For example, I can compute it for I equals 0 to 4 and j equals j inside 0 to 4. So it's effectively a loop that allows us to loop into a subregion. So what is the advantage here? The advantage is that because I'm going to compute this subregion, each of the time I'm going to read in this stripe and this stripe, right? And in order to compute this first element, actually I'm going to need the first element of A and first element of B. Let's say that this is to simplify this, let's say V equals 2. Okay, in this case, in order to compute this element, I need to read this element of it. and this element of B. Then in order to compute the second element, I still need to read the same element of A and the second element of B. In order to compute this element, I'm going to need to read this element and this element. In order to compute this element, I'm going to read this element and this element. You can find that interesting cases that when we're reading these stripes A and B, in order to compute 4 elements, right? Each of the inputs A and B stripes is being read twice because because for each of these elements in here, it's going to be needed for computing the output of all these results in here. So this helps in the sense that it helps to reduce the amount of read that we need to read the data from a global memory. And this is also called register reuse because we are normally reading data onto A and B, and we can reuse those data multiple times as we compute these submatrices. And this helps us to reduce the amount of load that we need to load the data from outside to inside. So usually this is a very helpful technique in most of hardware actually, in both CPUs and GPUs. So we're going to do that, and this program is slightly more complicated than our previous one. I'm going to walk you through that. This is our original loops. What we're going to do is we're going to try to split I, J, and K into 2 components, or actually in the case of IJ, we're going to split into 3 components, and then try to reorder them a bit, and then try to map it outside on the GPU thread. The innermost, remember that I want to keep this register blocking here. Okay, so let's walk you through this. So the first thing we're going to do is we're going to get the block C. Another thing that we're going to, because we're going to try to first run computations and store them onto local memory, I'm going to create a different stage called C local that we use to cache the computations on. And then what we can do here is we are going to split loop I and J onto 3 components and loop K onto 2 components. We're going to reorder the loop a bit so that they form a more like interleaved pattern. This is called tiling patterns that allows that forms the outermost loop in here, and then I1 the iterators and J1 and I2 and J2. One thing notice is that we're ordering J2 and I2 inside the reduction loop, and this is exactly to do what we call this register blocking that allows us to compute all the elements that's in the domain of I2 and J2 in here that correspond to effectively this direction can be viewed as I2 and this direction can be viewed as J2. And finally, we are bringing in this C local computations back onto this J1 loop. And then we're going to bind the outside loop onto the block indices in there. And finally, the decompose reduction try to decompose the original reductions onto a certain level. Okay, so I'm going to run this all together, and this is a resulting program. Actually, one thing that you can also try to do is you can try to run it interactively, so you will be able to perform a few transformations and use the IR module.show to see what is going on in each of the steps. But let's first take a look at this final program. You can find that it has a structure. First of all, if you go and look at the final output matrix, you will find that logically we're trying to divide it into small tiles. That's why we are calling it tiling, right? Divided into tiles, where the outermost iterators correspond to the block indices, and then thread indices, right? And finally, the innermost iterator correspond to the register tile block. In this case, V equals 8. And then this final program, first we initialize the corresponding say local regions, and then we are going to do a reduction that go and runs the local computation that adds back to say local, and finally this say local region get written back onto the global memory through another loop. So when we compile this program, this local memory actually will turn into registers in a low-level computation, because after we compact them, it's going to become an 8x8 region that can be transformed onto registers. Okay, so one of the things we can go and try out is we can go and try build this particular program. And in here, I'm trying to allocate the input data and output placeholders, and I'm going to run what we call time evaluator to evaluate the runtimes on this device. One of the common metric that we use to measure, how fast a program runs. Actually, we can print out, the milliseconds. Another way to evaluate it is to evaluate what we call a flops matrix. And this flops matrix measures how many floating point operations we perform per second. Right? So the evaluator will return the time that's will return the time that we take to run this particular computations, and this is a number of floating point operations to perform this matrix multiplication. There's a scaling factor of 2 because the multiply add actually counts as 2 floating point operations per multiple convention. So if we go and run this, you can find that you can get around 2 teraflops of computation, which is pretty decent actually for our first attempt. When I started to try to write GPU programs, if you go and naively directly go and map the stress without register tiling, likely you are going to get a lower number. Okay, so now we have talked about the basic technique. Let's come back to another technique called shared memory blocking. So one of the things that we want to notice is that originally, if we look at this program, we only take notice of these multi-level threading techniques, right? We're only trying to do optimization within a single thread. On the other hand, there's another thing that would really benefit in terms of GPU memory hierarchy is we want to be able to reuse the common parts that we read from different GPU thread within the same thread block. So in here, let's assume that each of the tiny block here correspond to GPU thread block, threads that within a thread block, and we have a L by L. Actually, these two L can be different threads within that GPU thread block. So in this case, in order to compute all the results in this L by L output, we will need to read in a bigger region. And you can find there's a common reuse pattern. For example, in this case, in order to read data for this block, we can go and get the input data from here and here. And then in order to read second block, you can find that you still need to read the same region. Right? So what we can try to do is we can try to go and fetch this 2 stripe of data onto the GPU shared memory, and then load from there to be able to help us reduce the memory pressure. And this is a technique called cooperative fetching. And the following transformation help us to do that. So it's a slightly longer, but it looks quite similar to the original piece of program. The main difference contains 2 parts. The first part is that we go and try to fuse these 2 thread index together and only bind to 1 thread index. This is just to simplify things so that you can either do 2-dimensional thread index and 1-dimensional thread index. They are usually equivalent. If you fuse them together, effectively you are trying to in the runtime you will decompose the 1 thread index using modulo and division onto the corresponding 2 indices. The second thing we're trying to do is what we call a cache read and cooperative fetching. So in this case, the cache read and cooperative fetching will try to go and take a block, like for example in this case, originally is A, read to C, and B. If I'm going to do cache read on A, I'm going to introduce a stage called A shared and insert in between. And remember that we still need to specify for A shared how we're going to read that. So what we're going to do is we're going to go and try to, first of all, find out loops in the reading cache actually, and then we're going to fuse the 2 loops together, and then we're going to split it by the number of threads so that we can spread it out over the threads. In this case, the second iterator is being bind as thread x. And finally, actually in this case, we're also vectorizing it so that this is another optimization that we can do. So when we are reading from the output memory, the global memory onto GPU memories, we can leverage possible, loading several floating points together if possible. If this code is a bit more complicated for you, don't worry too much. Try and play it with a bit. Remember that every bit of transformation will be able to use IR module.show to see what are the intermediate results, and that might help us to incrementally look at what's going on. But let's look at the final results of this shared memory blocking. And you can find that the main difference in here is that we have two additional stages that help us to go and bring in data from A to A shared and B to B shared. Another thing that I want to notice is that you can find, this loading happens inside the reduction, right? So that as we do the reduce, we are going to go and read the corresponding data onto those shared memories. And finally, because we are fusing all the thread indices together, so you can find there are some modular individual operations that try to redivide and get the indices out. Okay. So for this particular program, if we go and build that, you'll find that actually it will get much better performance, right? This number is at least larger than our previous number. It may not be the best on this particular GPU, but as a manual attempt, these two techniques kind of covers a lot of the common techniques that people use to optimize the tensor linear algebra program on GPU. So far, we talked about how we can manually write in the transformations on GPU. In the last few lectures, we also talked about how we can do automatic program transformation. In this case, we can go and do that using the metaschedule API. So in this case, we have specified the original workload, and it will run the tuning on the background. It can take a while, so I'm not going to show the final result, but you are more than welcome to go and try out this notebook and see what the final results look like. Usually, because we are not setting a smaller number of trials, so it may just be as good as the original manual version. But the takeaway is that it helps you to go and find out a possible optimized kernel using the techniques that we introduced just in the past few steps. Okay, so to summarize, today we started another axis of MLC, right? Up until now, we talk about how do we take models from machine learning frameworks onto an IR module? How do we go and transform them? But most of the examples so far only focus on the local CPUs that we have on the notebook. In this particular case, we switch gear to look at new hardware acceleration. In this case, a GPU. And modern GPUs are becoming more and more complicated. So, besides the normal threads and shared memories, there are additional concepts like tensor cores and specialized computing unit that we're going to touch in the incoming lectures. And depending on which GPU environment I use, a machine learning compilation process can help us to bridge that gap by bringing input models and try to target different GPU programming models and environments. We'll visit more hardware specialization topics in the future, and you are more than welcome to check out this notebook and play with it. And thanks, folks. This is the end of the part 1 today's lecture, and I will see you folks next week for the part 2 of GPU and hardware acceleration.